Hello guys, welcome back to this YouTube channel. So today we're going to talk about the quantum mechanical model of the atom. In the previous two videos, which predicted the timeline of the atomic structure, we talked about the classical model of an atom where the discovery of electrons, the discovery of protons, the discovery of neutrons by J.J. Thomson, Ernest Rutherford, and James Chadwick came to be for us to, know or have a feel of how an atom would look like. But earlier scientists, hopping into the 20th century scientists, decided to look at atom in a different kind of limelight, not as a classical limelight or a physically immeasurable object, but as a quantum species or as a quantum item, right? So how it went on to be was that we cannot talk about the quantum mechanical model of the atom without talking about the infamous mass spectrometer, because this device kind of kick off the race or the ball games or the theoretical predictions of how a quantum model of the atom would look like. Now, the J.J. Thomson, the first ever mass spectrometer was developed by J.J. Thomson. Yes, same guy who discovered electrons. The reason why he worked on such an amazing tool was because he wanted to figure out the mass to charge ratio of an atom or an electron or his positive rays or his whatever, right? Or of his experiment. That is how he worked on this infamous instrument. Now, this instrument now today has been worked on, improved upon millions of times, so it can be customized to fit whatever functions you're trying to make it do, right? But over here, what our focus is to figure out how it works. Our focus is to get the foundations of a mass spectrometer down before we move on to atomic mass, atomic weight, atomic number, mass number, all of that, neutron number, and then we can go to Maxwell Planck's and Niels Bohr's and Einstein's contribution into what we call the quantum mechanical model of the atom. So let's just hop on. For you to operate a mass spectrometer, it has 4 to 5 basic components. The first component is a sample chamber. The second component is the ionization chamber. The third component is the acceleration chamber and the electromagnetic or the deflection chamber. Now we have a detector and then a screen, which varies from device to device, but you do not need to memorize how it goes, how the chambers work. Just follow through with the understanding, and once you do understand it, it would always work for you. And then also, if you are prepping for the MCAT, this is a very high yield section on the MCAT. All this way until periodic chemistry is a pretty much high yield, so you want to pay much attention into what I am going to be explaining today. So first of all, you need to put your element or your sample into the sample chamber. Now the element you put them should be in atoms form, like an atomizer. As we already said, in Millikan's experiment, he used an atomizer. So something similar to spray your particles in here. The reason why it has to be in a form of an atom is because the particles has to go through different fields. And if it's in its elemental form, it will be hard to either ionize it or accelerate it. But depending on what you're trying to use it for, you can use a different sample on different spectrometers. But to our specific situation, we want it in an atomizing. So here can also be like an atomizing chamber or a sample chamber. So first you put your sample in, and after that, you run it through an ionization chamber. So what the ionization chamber does is that it either adds electron onto the atom or it knocks off electrons from the atom, basically making it an ion, either a positive ion or a negative ion. That is what happens in the ionization chamber. And how it works is that you have a base and then a bombarder, right? It's like basically a grinder inside the device. So when you spray your items in the grinder, hit on it, like it knocks on it, trying to kick off electrons, right? Set up free electrons so you can have an ionized atom, right? Which is an ion. So once it goes through the ionization chamber, the next chamber is the acceleration chamber. Now, how do you accelerate it? Remember, we have ionized it. So if we have ionized it, we can pass electric current to make it accelerate, right? So if we ionize it into a negative ion, we could just put a positive electric plate in front of it so that it attracts it and it zooms it, it makes it move faster, right? So that is where the acceleration chamber comes from. So basically what the acceleration chamber does is it makes the particles move faster through the mass spectrometer. Now, from the acceleration chamber, we go to the electromagnetic chamber or the deflection chamber. Over there, what it does is that the charges are sorted, or your ions are sorted from the biggest to the smallest, right? That was why the first function of the mass spectrometer was to determine the mass to charge ratio, like how much charge a specific mass would carry, right? So over here, it was separated into masses, and then we use electromagnets, so a combination of an electric field and a magnetic field. And you know from our previous discussion or the previous topics that electrons or the atoms or ions are affected by electric and magnetic field. So that is what happens over here. It's basically sortation. We sort them into various sizes. Now, once we sort them into various sizes, the particles descend down onto a detector. So we put a detector here, and what that detector does is that it has been programmed or it has been coated in a way that when a heavier ion falls on it, it registered a heavier charge or a heavier nucleus, or it gives some type of implication on the screen that there are some heaviness onto it. Basically sorting them out into how big or how small the ions are and then how much charge they carry. So that is basically the how a mass spectrometer works. One more time, let's go over it one more time. So first, your rule number first is sample, right, is placed in the sample chamber. And the sample could be atoms, ions, molecules, compounds, but in our case, we want atoms, right? So the samples are put into this sample chamber. In this sample chamber, the particles move to the ionization chamber, right? So what happens in the ionization chamber here is that the samples are bombarded, right? They are bombarded. They are bombarded to ionize them, to ionize them. And how do they ionize them? Because when they are bombarded, it kicks off electrons from the sample. And once you kick away electrons from the sample, it becomes an ion. So that is what happens in the ionization chamber. Then we go to the acceleration chamber over here. So what happens to the acceleration chamber is that the particles, or now the ions, are accelerated by using electricity, right? By using electricity, or in this case, you could say current. So that is what happens in the acceleration chamber. So once the particles move from the ionization chamber to the acceleration chamber, they are accelerated onto the deflector or the sorter, right? So once they get here to the sorter, they are sorted. So why does the electromagnetic and then the deflection chamber do? They sort the ions into different masses. That is basically what it does. It sorts the ions into different masses. It's the same thing that the deflection chamber does. So if there is like a heavier atoms coming here, it will just deflect it away, then deflect it, so that there are only lighter charges that comes towards here. And then the detector detects, basically that's what it does. It detects the size of the samples that lands on it. So once that is done, then it comes to the screen, and then the sample mass to the charge ratio is read on the screen. I'm not going to write anything on the screen right now because it's going to become important as we move on along the lines. Now you might say, what is the vacuum pump over here doing? The vacuum pump over there doing is to pump any unknown element or samples from the mass spectrometer, because we do not want our figures or our experimental values to be thwarted or to be distorted by an unknown variables in the chamber. So it will just pump away anything from it before you even put in a sample. So that is how the mass spectrometer works. Now, the mass spectrometer helps us identify a lot of things, right? It helps us identify sometimes atomic numbers, sometimes mass to charge ratio, sometimes the components of a compound, or sometimes the atomic weight of a specific element, right? So we are going to go through the fundamental qualities or quantities of an atom, such as the atomic mass, atomic weight, mass number, atomic number, proton number, neutron number. We're going to go through, and then we're going to take isotopes and discuss it all by itself. And then after that, we can go into Maxwell-Planck's and Bohr model of the atom. So let's move on to the next slide. Before we talk about mass number and then atomic weight, we need to talk about atomic number first. Atomic number. Into bracket, the symbol for it is Z. The reason why the symbol for it is Z is a Latin name. It comes from the Latin name. Is it a Latin or Greek name for Za, which means a number, a Za. So that is where the letter Z comes from. Za, a number. So it's basically atomic Za. So in today's word, atomic number. So the Z is stuck because after this, they had already variables that has the letter A. That is why they choose the Z. So the Z is it's called the ZA over here, right? So when we talk about atomic number, right, now pay attention here so that you do not get confused. Atomic number is the number of protons in an atom. It's what? The number of protons. The number of protons in an atom. In an atom. Now, do not get it confused, because in a neutral atom, in an atom that has not lost any electrons, the number of protons is equal to the number of electrons. So sometimes people would confuse atomic number as the number of electrons. No, it is not that. It is the number of protons. The number of protons is always constant in an atom, or in this case, in an isotope. We will talk about isotopes later on. But the number of protons are constant. You don't lose protons to get charged. You lose electrons to get charged. Electrons are the losable or the movable units of an atom. Protons are stuck. They don't go anywhere. They just sit there, right? So they are the determinant of an atomic number. So the number of protons that is inside an atom is its atomic number. Let's move on to mass number. Or before, let's move on to neutron number before we go to mass number. Neutron number. And then we could say the neutron number, we could demarcate it by n. So a neutron number is straightforward. Neutron number is just the number of neutrons in an atom. Is straightforward. Neutron number, number of neutrons. So there isn't much to talk about over there. So the number of neutrons in an atom, right? After mass, after atomic number and then neutron number, our next one is mass number. Now, hold on. Mass number is not the mass of the atom. They call it mass number, but put it in mind that it is not the mass of the atom. Mass number is just the addition of the atomic number and the neutron number. So in other terms, mass number is the sum of the protons and neutrons in the nucleus of an atom. That is mass number, the sum of protons and neutrons in the nucleus of an atom. So mass number equals to sum of protons and neutrons in an atom. Now we have our mass number. The next one we are going to look at is the atomic mass. Atomic mass. The atomic mass. Cannot stress it anymore. Atomic mass. Now, people really confuse mass number with atomic mass. They are different. Mass number is not the mass of the atom. Atomic mass is the mass of the atom. Mass number is never. Mass number is just the sum of the protons and neutrons in an atom. The atomic mass is the sum of the protons and the neutrons. But wait a minute, there is one more. And the binding energy or the mass defect of the atom. But weirdly enough, the mass defect, right, of an atom is sometimes equivalent to the mass of an electron. It is very tiny, right? So that is why mass number in some other cases could be approximate to atomic number, but it is not. Mass number is not the mass of the atom. Once again, atomic number is the mass of the atom. So atomic mass is the mass of the atom. So atomic mass is the sum. So when you think about the atomic mass, think about it that everything that makes the atom is it. So we have the protons, the neutrons, and then the electrons. But in this case, not the electrons specifically, it is the binding energy or the mass defect, right? That makes the difference. So it's the sum of protons plus neutrons plus mass defect. So the mass defect is when you sum up the mass number and then the atomic number. When you sum up the mass number, like the sum of the protons and the neutrons, it is not always equal to the atomic number. It's always like an approximation. So where does that approximation comes from? Like if you check, let's say carbon 12, you see it is going to be like 12.0012 something. That 12 something that it is there is the mass defect. That is where it is coming from. So atomic mass is the sum of the protons plus neutrons plus the mass defect. I put mass defect over here and I did not make it a basic quantity because as you move on in this chapter, you would realize that it is better to say plus mass defect than to say the number of electrons because almost always all the time you get to calculate for the mass defect, but barely at the time you get to calculate any mass of an electron or whatever. So when you find the mass defect, add it to the proton plus the neutron number and you get your atomic mass. That is how it works over there. Let's go to isotopes. Before we go to atomic weight, we have to talk about isotopes. So I'm going to clean this and then talk about isotopes. Now, when we talk about isotopes, do not make it confusing to you. Iso, the word iso, right? It's a Latin word that means constant or the same. Iso. So whenever you hear iso in anywhere, whether biology, physics, chemistry, it means the same. So think about isotonic solution, isotopes, isomers, isoelectronic series, isotones. If it has iso in it, it means something is being the same. Like, and then isobaric chamber, right, means the same pressure chamber. Isovolumetric. If we say iso, we means is the same. But over here, the iso means same. So are you gonna say the topes over here means what neutrons? No, topes is also a Latin word that means place. So isotopes literally translates to the same place, right? But the definition of isotopes is that they are atoms of the same element, So which means they have the same atomic number, right? So they are atoms of the same element, which means they have what? The same atomic number. What is atomic number? The number of protons. So they are the atoms of the same element that have the same protons or the same number of protons. But what differs? The only difference is that the number of neutrons differs. That is it. So it is the same element, the same number of protons, because if you exist in the same element, you should have the same number of protons because the element, the protons, determines what element it is. So you cannot tell me that you are an element number 47 but have the same number of protons as element number 13. If you are in the same element, you should have the same number of protons. Else it's a catastrophe, or nature don't work like that. So isotopes are atoms. They are atoms of the same element. Let me use colors to give you some type of a visual representation. Atoms of the same element. Same element with the same number of protons. Number of protons. But different. That is the key word here. Different number of neutrons. As I said, isotopes are atoms of the same element with the same number of protons but different number of neutrons. Or in this case, you could say different mass numbers. If the neutron number keeps on changing, the mass number also would keep on changing, right? We are going to work with three isotopes so that we build your understanding of how isotopes are. We're going to work with hydrogen, carbon, and oxygen, right? Each have three different isotopes. So hydrogen has three isotopes. The first one is called a protium. And then the second one is called deuterium. And then the third one is called tritium. So these are the three isotopes of hydrogen. Now, mind you, anytime you are writing an atom, right? Or an isotope, let me put this one. You already seen an isotope over here. So let me erase this and make an example out of it so that you get this ingrained in your head. If X is an element, let's say X, because, we like using X. Some of you miss your X's. So, so let's say X is our element. We have an element called X. Now our element X has an isotope, right? Let's call it has isotope X1, like this, X whatever is the isotope. If we want to represent the isotope, right? First of all, the mass number, right, which is the sum of protons and neutrons, goes up here, and it is demarcated by the letter A. It goes on the left side of X as a superscript. It does not go here, it does not go here. It goes up here. It doesn't go here either. But then the atomic number, which atomic number, when I was explaining, I said it had the symbol Z, because Z is a Greek word that means Zar. Zar means number. So it's atomic Zar or atomos Zar, right? And it goes down here. So this is how you represent an isotope. So this becomes your what? And then this would become your mass, your proton number. Let me put it there. And this 10 right here, this X is your element or your atom or whatever it is. So this is how you represent an isotope. So if I say carbon 16, you have to write C is the chemical symbol of carbon. But then the 16 that we say, the letters that we identify the isotopes by, or the numbers that we identify the isotopes by, like carbon 16, oxygen, whatever, or like carbon 14 or oxygen 16, that number is the mass number. That number is what? The mass number. So it goes up here, or in this case, called atomic mass or mass number. It goes up here. And then we all know, let's use carbon 12. So the 12, like if I say carbon 12, the 12 is the isotopic identifier. You put it up here, then you put your atomic number down here, which in this case, carbon is atomic number 6. It goes down here. And it works for every element that you take. If you take, let's say, oxygen 18, O for oxygen 18, and then what is oxygen atomic number of? Atomic is number, oxygen is number 8, right? It goes there like that. So that is how it works. Now the three isotopes we are going to be working with, right? Let me take this out of here. So we're going to be working with hydrogen, carbon, and then oxygen. Protium, which is hydrogen 1, it has one proton. The proton can't change. It is constant through any isotope. So it has one. So if it has one protons, and then we identify this as the mass number, which is the sum of the protons and then the neutrons, then what number that if we add to 1 would get us 1? 0. So that means hydrogen 1 has no neutrons, right? Let's take hydrogen 2, for example. We're going to go through all this, so maybe at the end you'll figure out how it works. Hydrogen 2, right? The 2 is the mass number. Once again, the mass number is the sum of protons and neutrons. So mass number equals to protons. Let me just say protons plus neutrons, right? And in this case, we have a mass number of 2 over here. And we know we're dealing with hydrogen. And hydrogen has atomic number of 1, right? Which is also the proton number. So 1 here. So in this equation, what number should this be to make this 2? It should be 1. So you add 1 plus 1, you get 2. That's how it works. We take tritium, which is hydrogen 3, right? The 3 is the mass number. And once again, we're dealing with hydrogen. The proton number don't change. It's still 1, right? 1. So what number should we add to 1 to get us 3? 2. So the neutrons here would be 2. And then you add it to get 3. So you see that in each case, the neutron number is being bumped up by 1. So the neutron number is changing. The proton kept on being 1. It's never changed. The same thing with carbon 12. Let's put 12 here. We know we're dealing with carbon. Carbon has 6 protons because it is atomic number 6, element number 6. So it has 6 protons. What number should we add to 6 to give us 12? 6. Now that is a neutron number. So 6. Let's try carbon 13. Carbon 13 works the same. Protons is still 6. What number should we add to 6 to give us 13? 7. So the neutron number changes. If we take carbon 14, it works the same. We know that carbon is still 6. And we have 14 here. What number should we add to 6 to give us 14? 8 neutrons. So you see, in each case, this is constant, but this guy here keeps on changing. He is determining, he is the variable here. The rest are constant. So neutron is the variable in isotopes, and he kept on changing and changing and changing. So what I want you to do is to do the exact same thing for oxygen. I drop it in the comment section. I'll be going through it to see if you got what I mean. So that is what isotopes work. Now that we figure out how isotopes work, I want us to draw our attention to what we call atomic weight. Atomic weight. Many people, myself included, or most people, when we hear the word weight, first thing that comes into our mind is gravity and mass. But gravity has nothing to do with this weight, right? Don't know why the scientists decided to give it the name weight, but gravity has no any factor here. But let's dissect it. When we talk about the atomic weight, we are talking about the average mass of the various isotopes that an element has. So if an element has three isotopes. If we find the averages of their isotopes, is when we get the atomic weight. So atomic weight is the weighted average of the various isotopes of the same element. That is the atomic weight right there. So when we weigh them, then we find the average weight. That is how we determine the atomic weight. Now, you would think, or the average person, or we would think that, okay, we know how to calculate averages. If I want to calculate the average of hydrogen, the atomic weight of hydrogen, I could just go 1 plus 2 plus 3, which will give me what? Divided by 3, which will give me 6 divided by 3, which will give me what? 2. And then I'll be like this. But no, if you look on the periodic table, the atomic weight of hydrogen is like 1 point something. It's not 2. Same thing with carbon 12, right? I could also be like, it is 12 plus 13 plus 14 divided by 3, which will give me any number over here, any number very close to the middle one, which is going to be 13. So anyone that you make, you're going to find the middle number to be the average. But no, it does not work like that. Let's take the car company like a Toyota to represent an atom. And let's assume that Toyota churns out 2 cars. They only make the Toyota Corolla and then the Toyota Camry, right? If these 2 cars is what the company makes, and if we want to find the average cars that they make, we could just add the number of cars of Corolla, Camry divided by 2. It will give us the average. But no, let's say the Corolla over here has higher specs. It has lane tracing, it has theft protection, like the technology in it is packed. So that car is expensive. So let's say a Corolla costs $100,000. And because it is expensive, the company don't make a lot. Let's say about 5% of the cars that the company make is Corolla. So let's say they make 5%. And Camry, let's assume, is a street vehicle, just key to start. Regular car, doesn't even have AC. It is cheap. A Camry costs $5,000. But because it is cheap, that is what the consumers usually buys. So 95% of what Corolla produces is Camry. 95%. So if at any point in time, I tell you to go to the street and find me a Toyota car, do you think that the chances of finding a Toyota Corolla is going to be the same as finding a Toyota Camry? No. You're going to find Toyota Camry everywhere on the streets, but rarely are you going to see a Corolla. That is how atomic weight and isotopes work. If I take the hydrogen atom, for example, if I take the hydrogen atom, and it has hydrogen 1, hydrogen 2, hydrogen 3. But hydrogen 1 is like 95% of hydrogen, and then hydrogen 2 is, let's say, 2.5%. These are rough figures, by the way. And hydrogen 3 is also another 2.5%, right? So at any point in time, if I tell you to find me a hydrogen atom, do you think the chances of you finding hydrogen 2 is the same as finding hydrogen 1? No, hydrogen 1 is going to be everywhere because it is in abundance. Hydrogen 2 and 3, rarely are you going to see them. That is how isotopes work. So if we say calculate the atomic weight, we don't mean the literal average. We mean the average according to how much of the substance you can find just by plugging it from nature. That is it. Now, let me use an example for instance, like a real life example. Take uranium, right? Uranium has three isotopes, just like hydrogen, right? The uranium that could be used to make an atomic bomb is just one isotope of the uranium atom. And that makes up about, this is a raw figure by the way, about 0.2% of the entire uranium atom. So if you find a uranium core, the amount inside there that you can use to make like a nuclear bomb is 0.2. It's very few, minute amount, right? So that is why when scientists are trying to purify uranium to make a radioactive plant or whatever, they have to build this whole refinery process, because there is no way that you're just going to find that isotope of uranium lying around. No way. You got to dig into the uranium core and find, because it's just a tiny, tiny fraction of it. That is how isotopes work. The comment section or on the screen, and then you can work through it. But let me show you how you can calculate through it. I will give you the general formula so you could go up with it. So if you want to find any isotope, like any atomic weight, the atomic weight will be equal to, so the the percentage abundance, right? The percentage abundance of like an isotope let's say one of the same element plus the same thing, the isotopic abundance of isotope 2 of the same element, all the way to how many ever infinities it has. There is no division when you are calculating the averages, the atomic weight. When it comes to its calculation, you don't divide anything. You just sum according to the percentages. So you find the percentage, you add them up, and that gives you the isotopic abundance or the atomic weight of the specific element. So from here, we are going to go through Maxwell Planck and then Nell Bohr, how they contributed to the quantum mechanical model of the atom. So we will branch off here. Not completely veer off, we're going to build upon it. That is why we had to go through the mass spectrometer in the first place. So let's move on to Maxwell Planck and then Nell Bohr.